Hello everybody, it's time for video 4, our last video in lecture module 2. In this video, we're going to continue our discussion about Earth, and we are going to move into Earth's surface. What does it look like? What processes change Earth's surface? And by extension, what processes can change planetary surfaces in general? And then we're going to look specifically at something unique on Earth, the so-called plate tectonics, a constantly shifting of the surface of the Earth that is making Earth's surface change more rapidly than any other planetary surface that we see, and it is a unique process. Let's go ahead and get started. So in today's video for video 4 in module 2, we are talking about Earth's appearance and plate tectonics. What we are going to cover are the surface features. What do we see on the surface of the Earth? The oceans, the continents, polar caps. And if you're looking from outer space, you are going to see that there are lots of clouds in our atmosphere. Something that when we talk about Jupiter and Saturn, we pretty much only see the clouds. What are the primary processes that change a Earth's surface? Talking mostly about erosion right here, and plate tectonics, volcanism, all sorts of different processes, just tectonics in general, that really change the surface. And we will end by focusing on something unique to the planet Earth, or at least as far as we've now seen amongst all the planets that we've seen up close, plate tectonics. So let's take a look at Earth. This picture over here on the right is a very famous image taken from the Apollo 17 mission. And this is called the blue marble, one of the first pictures that we got where we could look back and see the Earth in its entirety. So here's a snapshot. You can see the entire continent of Africa right here. If you look closely down here, you can see Antarctica, and clearly we have oceans, continents, clouds, polar caps. So one of the things we'll talk about with every one of the planets that we go through are what are the major surface features, the major terrains is sort of the generic term I'm going to be using. So what sort of things do we see when we look at a planet from outer space? So we are in our spaceship, we are lucky enough to be astronauts, and we are looking down on the Earth's surface. One of the first things that we're going to pick out is we are the blue planet, the blue marble, as it's so sometimes called. That's because liquid water, our oceans, cover 71% of the surface. So 71% of Earth's surface looks blue when viewed from outer space. Now, I do want to be clear. I don't want people to get too confused and think that we are a water world. We are not. So while it covers 71% of Earth's surface, that is only about a tenth of 1% of all of Earth's volume. We are actually devoid of water if you think about it in the grand scheme of things. So the liquid water is pretty much only on the surface. And let's go ahead and really make sure this is clear. This is unique to everything we have observed in our solar system, everything we've ever observed. Currently, Earth is the only location in the universe that we know of. It's definitely not the only location in the universe, but it's the only one that we know of where that has liquid water on its surface. But our oceans are really not all that deep. On average, they're less than 4 kilometers deep, only 3.7 kilometers. And if you remember, all the way down to the center of the Earth is 6,378 kilometers. So this is just a little bit of the uppermost part. And our oceans sit on top of what we call oceanic crust. And then the oceanic crust is floating around on what we are going to call the oceanic tectonic plates. Stay tuned for plate tectonics. We also see that there's plenty of land mass. The majority of the rest of the Earth's surface is covered by land, rocky continents. And these things are covered with all sorts of wonderful things that you can study in a geology or geography class. They're covered with mountains, rivers, deserts, forests, tundras, cities. Humans have had a pretty remarkable impact on the surface of the Earth with our cityscapes. The continents are sitting on top of continental crust that's thicker on average than oceanic crust, and the continents sit on top of the continental crust on what we call continental tectonic plates. We also see that Earth has polar caps. They are changing in size throughout the seasons. They're growing and shrinking. We have not yet had a iceless summer, so the polar caps still remain, and they're made out of water ice. We have the southern polar ice cap highlighted down here. that sits on top of Antarctica and extends out into the Arctic Ocean or Antarctic Ocean as well. We have a northern polar cap. It does not sit on top of land. It is only ice that forms on the oceans, and that forms our northern polar ice cap. These are growing and shrinking seasonally, such that they're smallest in that hemisphere's summer, and they are largest in that hemisphere's winter. We will return to this idea when we get to Mars, because Mars too has polar caps. A little bit more complicated than Earth's, and maybe a little bit more exciting. And then finally, we can easily tell that Earth has an atmosphere. It's easy to see in a lot of the images from space. And even though it's not readily apparent quite in this image, you can easily see that we have clouds floating around in our atmosphere. So if we were flying around in outer space, it'd be one of the first things that we know. And we can use the clouds as tracers to see how our winds are moving about. So it reveals all these wonderful atmospheric wind patterns that are going on underneath. Our trade winds, thermal winds, our Hadley cells, meridional winds, all sorts of things that I've highlighted in green, so you don't need to know them, yet are quite interesting to study. And our Earth's surface is not static by any means. Out of all the planetary surfaces we're going to talk about, other than maybe the exception of Io, a moon of Jupiter, Earth's surface is changing the most rapidly. It is on geologic time, it is essentially never the same. It is in constant change. So what are the processes that are changing Earth's surface? And this is a primer for all the processes that we're going to consider that can change planetary surfaces in general. And yes, we see them all on Earth. So let's start with a rather generic one, a catch-all one that covers quite a bit. So things that can change a planetary surface: tectonics, a catch-all term that talks about any process that changes the structure of a planet's crust. So anything that changes the structure of a planet's crust is a tectonic process. On Earth, the main tectonic process we're going to talk about is plate tectonics. And plate tectonics is going to be a major topic, so I'm going to hold off giving you more details right now. But I do want to highlight that right now, as far as we can tell, plate tectonics appears to be unique to Earth. At least amongst the planets, there is an argument that you can make that looks like there might be some plate tectonics on Europa and Enceladus, icy moons of Jupiter and Saturn. So what else do we have that changes Earth's surface? Volcanism. This is where we have the eruption of molten rock, typically from the mantle or deeper. So we have molten rock, magma, as a subsurface, erupting and coming up onto the surface of the Earth. Once it reaches the surface of the Earth, we don't call it magma anymore, we call it lava. So this is actually, since it's changing the structure of the crust, you could consider volcanism as a subset of tectonics, but we're going to consider it separately because it's building new landmass, and it's one of these processes that we can see on the terrestrial worlds. On Earth, you don't need to remember this number, but we have about 1,500 active volcanoes that cover the Earth, and we can use those to actually map out plate tectonics, our plate boundaries. What other processes do we go on that change Earth's surface? Erosion, a process that changes the planetary surface. And this is the removal of landmass, so taking material from land and moving it from one location to another location. Typical view would be we are going to erode away mountains. We're going to take all the material on mountain chains formed by tectonic processes, and we're going to bring it back down. We're going to erode them away. So it's just the removal of landmass and transporting it from one location to another. Earth is rich with erosion processes, the most erosion of any planetary surface that we see, and that's because we have an atmosphere and we have liquid water on its surface, meaning that we have water erosion from a water cycle. We have wind erosion from the winds blowing around. We have chemical erosion, and there's even life-based erosion. So we have the most erosion processes of any planet, meaning that surface features don't stick around very long. One of the important ones that gets erased pretty quickly, making them relatively rare on Earth, are impact craters. So here is, if you go out to Arizona, you can see where something came from outer space and struck the surface. A meteoroid came down and created this nearly kilometer wide impact crater, this bowl-shaped depression on the surface of the Earth. So yes, uh, planetary surfaces still get hit from leftovers from outer space, and they leave a impact crater. On Earth, we've only identified about 200 of them because they get eroded away pretty quickly with all the water and wind erosion. When we look at the moon is dominated, its surface is dominated by craters. All right, so let's look at Earth's unique tectonic behavior, a process that is constantly changing the surface of the Earth. Plate tectonics, a relatively new idea as well. Whenever it first was proposed, that the surface of the Earth, that you could basically take the crust of the Earth and break it into a bunch of different puzzle pieces, and these pieces are all moving and jostling about, running into each other, like colliding this way or sliding past one another, diving underneath, spreading apart from one another. That idea was originally thought to be laughable, and the person that proposed it actually got laughed out of conferences. Turns out that person was correct. So, plate tectonics, the fact that the entire surface of the Earth is constantly moving around, is a form of tectonism where we break up the entire surface of the Earth into individual plates, tectonic plates. You can think of taking the globe of Earth and making a jigsaw puzzle out of the surface. Each one of the puzzle pieces can move around, which gives us two different types of tectonic plates. The ones where we see land masses, the ones where the continents exist, continental plates, and then the tectonic plates that lie beneath the oceans, oceanic plates. These are not static things. They are constantly moving around. We're going to see that the mantle is in constant motion, constant convective motion, which it causes these plates to constantly move. And if the plates are constantly moving, all the surface features are constantly moving. The locations of the oceans and the continents are constantly changing. Not very fast by human standards. Centimeters per year is pretty fast spread, but enough where we can measure it with GPS, and we can measure it even before GPS. I just want to show you one just beautiful example, and something that's on my own personal bucket list is I would love to go diving out here in Iceland, where you can go to what's called the Mid-Atlantic Ridge, where you have the continental crust, the North American plate, and then you have the European plate, and they're sitting in the middle of the Atlantic Ocean, and they are slowly spreading apart from one another. And as they spread apart, material rise up, creates this ridge that goes all the way through the Atlantic Ocean, easily seen. And this is called the Mid-Atlantic Ridge. It runs right through Iceland. It's the landmass that it runs through. So in this picture right here, we have a diver that is underwater, and this is the North American tectonic plate. This is the Eurasian plate. So they are between North America and Europe right here. And every year, this gap widens by about 2.5 centimeters per year as the two plates separate apart from one another, and so-called continental drift. Where the continents are is constantly drifting and changing. A very, very unique process. We see this only on Earth. And while we don't know why we only see it on Earth, a very, very strong piece of evidence, it seems like water, liquid water on the surface, and a good bit of water in our mantle is probably one of the factors that's most important. But we do not know exactly why we don't observe this on other planetary surfaces. So I want to just go ahead and give you a view of all of this. So here is a map where you can see the continents, and now you can actually see the ocean floors right here. If we go all the way up right here, you can see this ridge. And this is our Mid-Atlantic Ridge. There it is going through Iceland. And here's that person hanging out as those two plates separate from one another. So we can map out and we can look at all the plates on the Earth's surface. Prior to more advanced technology, there's an easy way to map out the plate boundaries, and that's where you have these continental plates. So you can imagine as plates rub against one another, collide with one another, separate from one another, you're going to get a whole host of geologic activity. Plates grinding past one another, that's going to generate a lot of earthquakes. So you can see by the location of where earthquakes are, They're going to be mapping out where plates are grinding against one another or running into one another. Also, these are the locations where you are going to see most of your volcanoes. So if you have a crack in the crust, a gap in the puzzle pieces of Earth's crust, it gets pretty easy for magma to come up through there. So it's a natural location for volcanoes. And what we're seeing actually on this picture right here is each one of the red dots is a volcano on Earth. And you can map out, you can see what's called the Ring of Fire. So right here, you see lots of volcanoes, and here's the other half of it. This is a so-called Ring of Fire. So you can use this, and it's really mapping out plate boundaries. We can also put these white arrows on here, which is showing the direction and how big the arrows are, showing how fast those plates are moving. Uh, so you can see the direction that they're all moving in. So we can map out where all the plates are. And we have our continental plates, we have some oceanic plates. I'll show you a few more images. But one point I want to make clear, so you can go ahead and put this in your toolbox of how we can investigate planetary surfaces, is Earth has plate tectonics. And where there are plate boundaries, you will naturally get volcanoes. So one of the things we can do is we can look at the distributions of volcanoes on planetary surfaces. And if we see them clustered like they are on Earth, outlining the plate boundaries, that's evidence for plate tectonics. If the volcanoes are just sort of spread out evenly over the surface of a planet, then you're not seeing any evidence of plate boundaries. You're not seeing any evidence for plate tectonics. Something that we will actually investigate when we look at volcanoes on Mars and volcanoes on Venus. I just want to give you a couple more images. So here is a cartoon map that makes it a little bit more clear, where you can see all the different plates. So here's that North American plate. Here's the Eurasian plate. There's Iceland. It goes right through that landmass. So these are all the plates. I just wanted to give you a easier to view map. You don't have to memorize any of these plate names. And I want to give you not only an easier to read, but perhaps a harder one to read that's a little bit more detailed. So here you can see a very detailed map of all the tectonic activity and really the plate tectonics, and you can see that all the plate boundaries. So what is driving plate tectonics? One, we need the crust to be broken up into these plates. And now that we have these plates, what's causing them to move? And to do this, we have to go back and review a concept in physics about how we can move heat around from one location to another. So there are three primary methods to move heat around. You can move heat around by radiation, light. So you can, we all can go outside and get blasted with some sunbeams and we feel warm. So you can clearly move heat energy via light. Then that would be radiative way. Convection, this is why you don't want to go touch a hot stove surface. Conduction. Conduction is transfer of heat through two things touching. So if you have a metal bar, you put it in a fire, the heat will creep up the metal bar via conduction. And then the last one, what we want to focus on, and is going to become a theme for understanding planets, is a method of transferring heat called convection. So convection is the transfer of heat from one place to another through physically moving a liquid or a gas from one location where it's being heated, moving it to another location that's cooler. It's a little bit more specific than that. And what I want you to do to picture this is, let's imagine a pot of boiling water. The bubbles themselves are not convection. That is forming gas bubbles, steam bubbles. But what about the motion of the water itself? So here we are, we're heating up this water from the bottom. The water is going to warm up. As you increase the temperature of things, things expand, become less dense. So as we heat up this pocket of water, or this pocket of air, if you want to consider our atmosphere, or this pocket of liquid hot magma, if we're talking about interior on the inside of the Earth, it expands, becomes less dense, which causes it to float. So it's going to float up, and then it'll reach the top, moving that heat upwards, and then it'll eventually reach some sort of a top where it can cool down, transfer that heat to somewhere else. Whenever it cools down, it's going to contract, so it's going to become more dense and sink back down to where we have something that's warming it up. So it'll warm up and rise again, cool and sink, warm and rise, cool and sink. And naturally, what it'll do to most efficiently transport the energy around is you'll set up these nice little units of convection where you have warm rising here, cool rising here. That would make up one what we call convection cell, this cycle of convection. Next to it, we'd have another convection cell. And notice that the warm part, the rising parts match up, the sinking parts match up. So here's another convection cell. And now down, down, the sinking part, the rising part. So you'll set up a series of convection cells. And notice that you have rising up, but then at the top, you have side to side motion. So when we actually look at the interior of the Earth, it's hotter deeper down. We have heating from the bottom, and then the upper part of the mantle is actually an amorphous solid. I know that's a fancy term, but what it means is it's a solid that can flow, it can move, it has some measurable viscosity. So convection can occur in it. So we're getting heated from below, and then that material is going to rise up, and then it's going to move laterally side to side, and then it's going to sink back down. So just beneath our crust, the upper part of the mantle, and actually technically the bottom part of the crust, we have these convection cells going on, where hot material is rising, moving over, and then sinking back down. Our plates are riding around on top of these convection cells. So whenever the material is moving this way in the mantle, it's dragging the plate. The plate is like a raft floating on top of it as it gets moved, causing the entire, if this is a continent, the entire continent to drift, to move along with it. So we have all of these plates that are riding on top of these convection cells. Where you have motion this way and then motion this way, you'd have these two plates that would collide with one another, and the oceanic plate will dive underneath the continental plate, what we call a subduction zone. This is not a geology class, but that's what you're seeing right here. We go out into the Atlantic. So this is a case where we have a plate moving this way, we have the other plate moving this way. So we have, say, North America, the North American plate moving this way, the Eurasian plate moving this way, and the plates are literally getting spread apart from one another, and you'll create, say, the Mid-Atlantic Ridge. So this is what's driving plate tectonics. This is also, as all of these plates move around and jostle and bump into one another, generating lots of earthquakes, which are giving us all those seismic waves, which have allowed us to go ahead and map out the interior structure of the Earth. How does this actually play out? I love sharing this bit of information. I just find this so fascinating. So hopefully you do too. If the continents are all moving around and we can actually measure how fast they're moving very accurately now with GPS, we can measure it before as well, but we know where all the plates are. We know what directions they're moving. We know what the Earth currently looks like. And maybe you've noticed that the eastern part of South America really looks like a side of a puzzle piece that fits very well with the western part, or the western part of Africa. Then we can take the continental drift and we can rewind it. We will see that South America and Africa, they used to be connected. They were one larger landmass that got separated from one another. So why don't we turn back the clock and see where the continents, where the land masses used to be, where the oceans used to be. So we can do that. And if you rewind the clock, there's our Jurassic period, go Jurassic Park. You would notice about 250 million years ago, all the land masses were together in one giant landmass that we call Pangaea. And then if you kept rewinding, Pangaea would have separated. If you keep rewinding, it would have come back together. It would have separated, come back together. So this is likely a recurring pattern where there have been multiple Pangaeas. If you go to the future, then we will run, all the continents will run back into one another, and we will have future Pangaeas on the timescales of hundreds of millions of years. And some really great evidence that really helps solidify and have people understand that plate tectonics is a process that's happening is it really resolve a lot of fossil record things where we see fossils in Eastern South America. We see the same fossils in Western Africa. How can you get the same fossils a ocean apart? Well, you rewind time and when there was not an ocean between them and they were actually connected. All right, so I want to end with this video so you can see Pangea becoming the current map of the globe. You can watch the continental drift over time. This is 140 million years. You have outlines of the current continents. This is actually running quite slowly. As you can see, we have to go all the way to 120. So I'm going to leave this up, but this is the official end of this video. This is the end of lecture module 2. Now you can see these continents separating. So thank you for tuning in. Go ahead and make this full screen on the PowerPoint version of the slides if you want to watch it a little bit faster. Since I'm screen sharing, it is going a little bit slow. Thank you for tuning in, and I will see you for lecture module 3.